late lunches trickle in. But anyways, we're really glad to have you here. You have Elizabeth Carlson here for Jake's seminar today, and yeah, talking about data assimilation and parameter recovery. So please take it away. The floor is yours.
Thank you. Yes, so today I'm going to be speaking a bit about my PhD thesis work that's kind of been extending into, you continue working on it after you graduate and everything. So this is kind of an outcropping of what I originally started working on for my PhD, and I may mention a few extensions as well as we go throughout. But I specifically want to focus today on the concept of data assimilation and parameter recovery, which is quite a difficult problem. You know what? We're just going to do this.
You try just clicking the slides.
There we go. Okay, great. Sorry. So, first, we're going to just put a brief outline on what we're going to be discussing today, which is what is data assimilation. We're going to talk about a new data assimilation algorithm, new as in 2014. Most of the data assimilation algorithms were invented in the 70s and 80s. And then we're going to talk about some specific theoretical and investigations and computational in an idealized setting. And we may potentially also look at a large scale application as well in Assimilation, depending on how far we get. And we'll talk about other current and future work. So specifically, I want to talk about what is data assimilation. So the fundamental point of looking at these fluid dynamic systems is that we want to model physical phenomena, right? For example, the ocean or the atmosphere, something like this. So the problem with these is that we are writing down a model that is a differential equation. So we need to initialize our model somehow. We're usually considering like some sort of initial value problem. So I want to model physical phenomena. I need an initial value that is defined everywhere in space. This is problematic if I'm looking at something like a wind field. For example, look at this second picture in the corner here. I want to measure the field at every point in space if I want to initialize properly. That's not possible. However, I can take measurements at discrete points in space, and I can do it over a large amount of time. So an initial value problem, I need one time, all space, but what I have is some space, some time. So the question is, how do I use all the information that I'm being given to actually better model the problem that I'm trying to solve? So this is the broad idea behind data assimilation. We want to incorporate these observational measurements and all the data that we have into the model. Now, of course, data is messy, it's noisy, so we commonly use probabilistic methods. These generally fall under two branches, common filter nits variance and 40-var nits variance. The idea is data assimilation is meant to address the near possibility of obtaining this correct initial condition, and it's also used to help minimize error from the model physics. And we're going to use data to adaptively correct the model. So the big idea is this, and this is actually the big idea underpinning all of the data assimilation models, but this one is made theoretically rigorous. So a version of this data assimilation algorithm was invented in the 70s. It's called nudging. It's the very first data assimilation algorithm. This is the first attempt to put it on super rigorous ground. So we're going to define U of t to be the solution to this distributed dynamical system. So think du dt equals f of u, where f is the right-hand side of the Navier-Stokes equations, for example, incompressible, with missing initial data. So this system, we know how it's evolving physically, and we can observe it in time, in discrete space, or maybe even more easily think about analytically a finite number of Fourier modes. We can observe those. So that I can observe. So I'm going to observe those as a fixed point. So if I go back here, these are the points at which I observe. So I'm going to take these points. So I should use these points at these weather stations, for example, and I'm going to interpolate the data between them so that I get a full field approximation of the observations, right? This is a terrible initial condition because of sensitive dependence on initial conditions for chaotic and turbulent systems, but it's fine if we need to, we need some sort of representation all over all of space. So we're going to take IH of U of t to be this representation. So we don't know U, but we can know IH of U. From here, we're going to construct the system dv dt equals f of v, where f is the model physics plus this feedback control term. And we're going to initialize with any initial condition. And I'm going to explain to you, this does not end up mattering. What we pick for the initial condition now no longer matters. So what is this term and what does it mean? So here's kind of a very basic 1D caricature. Let's say these blue dots are observations. So we've got 6 observations here, and I'm going to interpolate those observations linearly. And when I do so, I get something that's continuous in space, right? So my V, supposing I have a solution to this guy, gives me some sort of curve in space, right? So I want to look at the error between V and U, right? I want to drive V towards U, because U is the system I actually care about. I don't care really what's happening with this guy. I want to know U. So if I want to know U, I need to look at the error between V and U. But the only way to do that accurately is to look at IH of V minus IH of V. And this is important for later in application. A lot of people in application for old nudging schemes did V minus IH of U. This causes problems. So I want to look at IH of V minus IH of U. If V is too high, I want to drive V, say, at the next time iteration down towards U. So I want this guy to be negative if V is above U. So that's where this negative sign comes from. And then mu is just a positive relaxation parameter that drives it farther. So if this error is small, I want to drive it really fast. So I'm just going to shove it towards, I'm going to make the time derivative go much larger. This is the underpinning and the fundamental idea behind this data assimilation method and all data assimilation methods in general. But the nice thing about this, as it's written, is that if you're just implementing this straight up, this is in a computational setting very easy. You're just adding a term to your PE, right? You don't have to deal with tangent linear models, adjoints, or ensembles. A lot of those data assimilation algorithms, they should and they do use a lot of ensembles to kind of deal with the noisy part, because there's a lot of linear approximations that come in. It's quite a mess. But the nice thing about this is the main computational expense is due to reading these data sets. This is very interesting. This is very good. Makes our data assimilation algorithm simple. Yes.
Right, so is there possibly noise in the measurement?
We'll come to that.
Okay, sorry.
Yes. So I want to discuss briefly, this slide is just to mention that the IH theoretically that we need is very simple. We just need it to satisfy for Dirichlet periodic boundary conditions. This bound here, this is a bound. There's another bound as well on L2 and H2 that you can find in a finite element textbook. But basically what I need for the theory is I need this bound. And the examples of interpolants that satisfy this are very nice interpolants that we like, Fourier truncation and piecewise constant interpolation in 2D. So these and linear interpolation, for example, these things are all good, they're all nice, that's all we care about, that's what we use in real life. So IH is nice even in a real world setting. So my setting in particular, theoretically, that I've been sitting in for the last few years is the 2D incompressible Navier-Stokes equations. So if we put this into the data assimilation framework, here's the model, the top here is U. We want to model, we want to find out what the solution to this system is. We don't know U naught. So instead we construct the V system, which is Navier-Stokes plus this feedback control term with some arbitrary initial condition. It just has to be sufficiently regular. That's the only criteria. So Azouani-Olson-Titi proved in 2014 was that if my measurements are close enough together, so I have enough measurements, and I kick the error, if I take that mu and I make it really large, so I'm kicking it as hard as I can towards the true data, then I get exponential convergence eventually, so long as U is only is close to the attractor. So I'll get exponential convergence in time of V minus U in both L2 and H1 modes. Now this is really powerful and really interesting, but it's like one of the first rigorous results in a continuous setting, not a stochastic setting for data assimilation, which is really neat. So in an idealized setting, this is where we want to play with things, this is where we want to make things more robust. So in theory, mu has to be order Grashof squared or Grashof log Grashof, which is huge, and H has to be like 1 over mu, which is super tiny. In practice, this is not necessarily the case. So here's an example of a solution of the Navier-Stokes equations. And so this is this reference solution U that we want to use. This is our proxy. Okay, so that's what we want to recover. So we're going to take observations of this. We're going to take them continuous in time, and we're going to observe at a finite number of points, and we're going to constant piecewise interpolate. So that satisfies our IH bound that we had a couple slides ago. So this is our approximating solution. So you can see it starts out kind of wonky. It started with a 0 initial condition, but it's already starting to capture some of the physics going on underneath quite quickly. So I want to go to the next one here. I should have put the truncated version of this video in, so it always goes a little bit long. So this is the one in slow motion. I really want to get to the one in large motion. So see 0, and then we're already starting to get pretty quickly, we're starting to get some of the large scale structures coming pretty quickly.
So on the theorem on the previous slide,
Yes.
you said there's something about there exists a mu greater than 0 so that the convergence is exponential.
Yes.
Does the rate depend on mu? It seems like it would based on, okay,
Yes, yes. So you'll get it from the Brownell on body kind of.
cool.
So this is everything including error. So here at the top right corner is our exact solution. That's what we want to recover. And then these are our observations, continuously in time. Notice there's only 49 of them. That's not that many. And mu, I believe in the state of simulation at the beginning was like 24, which is not Grashow, or Grashow squared. So here's our approximation. So we're assimilating this into this simulation. So we're assimilating for everybody online this into this simulation. And so this is the error plot of these two graphs on the left, bottom left corner. So black means we've reached machine precision. And so for these nice, beautiful, idealized computationally idealized problems, we have exponential convergence. They happen really nice, they happen really fast, and it's beautiful. So from here now, of course, this is our beautiful mathematical, theoretical, analytical land. That's great. What happens in the real world is we're going to get these measurements, we're going to get them discrete in time. And we're going to get the measurements are going to be noisy. We might not be able to observe all the data on the domain, blah, 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 blah. So turns out that it's relatively robust to all these sorts of things. Each one has been analyzed specifically. First off, I want to mention that this has been done for a variety of dissipative equations. The fundamental reason this works is actually because of this property of dissipative systems known as finite determining modes or nodes. So that's the whole fundamental underpinning here of why everything theoretically works. If we have noisy data, we'll get convergence up to an error determined by the covariance of the trace of the covariance matrix. If we have discrete in time, so long as they're not too far apart, we still get the exponential convergence to 0, which is nice. So it tells us that it's not restricted to this continuous in time choice. We can also show that it was recently shown theoretically, computationally in this paper, theoretically in this paper for Lorenz solutions for 3D Navier-Stokes that we still get convergence with this data simulation algorithm. Most importantly, the 2D data for a 3D system, for example, think the ocean. I can take measurements on top, I can have buoys going everywhere, but getting observations down farther deep into the ocean is a lot more difficult. So this theorem is actually very promising in general for, okay, if I have just a 3D system and I'm just observing the top layer, I can still get some sort of convergence. Similarly, if I have data on a subdomain, I should actually have added on here, there's more papers by my academic brother, Colin Victor, and my advisor, Adam Larios, on moving observers. So if our observations are moving in space throughout time. So that basically changes our observation grid throughout time. Of course, we want to look at numeric approximation or model error, and we also want to look at some atmospheric and ocean applications. So basically the idea is we have this beautiful theory, we need to make it robust, right? So one of the aspects of robustness that I focused on early on was what if we don't know, say, the viscosity parameter in the Navier-Stokes equations. So here's my original system with some viscosity that I don't know. So I don't know nu1. So instead of, and I don't know u0, that's per usual, right? So now I'm going to take my system and sorry, I have not clarified this yet. This system, this data simulation algorithm is called the AOT algorithm in honor of Azouani-Olson-Titi, who invented it in 2014. Or CDA, but CDAs can be a bigger umbrella for nudging, grid nudging, and spectral nudging as well. So if we're looking at dVdt, we want to look at this physics is evolved similarly, plus the feedback control term, and then we have this viscosity change. We don't know what the true viscosity is, so we're going to estimate it. So, and then we're, of course, as usual, going to give it any initial condition that's sufficiently regular, we like to state with 0. So we can follow a similar analysis, which is this nice standard energy estimates, to show that the error in the L2 and H1 norms, as you send t to infinity, is controlled by the error in the viscosities. So of course you recover the true result when nu2 equals nu1, right? So the original result says this converges exponentially fast to 0. So when nu2 equals nu1, we have 0, we're done. So this is exponential conversion up to this error. All right, nice, fine. What does that mean for us computationally? So this actually led us into like, okay, we want to do this, we want to supplement it with computations. How sharp is this bound? So that leads me to this graph, which, pardon me, it's an old graph, so it's not the best. We basically said, okay, 10 to the minus 3 is my true viscosity I'm pretending, right? So I have this proxy simulation I'm running, and then V is agnostic to it. So I'm going to take V with some approximate viscosity, and I'm going to see how the L2, the large time L2 error of the IHW is controlled by that bound. And I can say that because remember my bound on IHW is controlled by the W in H1 norm. That was an assumption I made on IH beforehand. So IHW also is attained by this second theorem. It's bounded up by this quantity via the second theorem. What we see here is that if I choose that C, which of course in theory is large, around 4 or 5, it actually seems to be tracking the IHW norm relatively well. So this gives us the idea, if in practice this actually seems somewhat sharp and characterizing, I guess I should say, can we solve for the true viscosity? Can we recover it? And can we do so live computationally? So this is when we came up, and this was originally one of the idea of my co-authors. This is our first paper. The heuristic for recovering true viscosity is to look at the two systems, right? So if I have a U system, right, in theory, I can look at both, right? And I know everything. Computation is the problem. So if I look at V minus U, right, I'll come up with this equation, this top one, right? So W is V minus U, or U minus V, it doesn't matter, all the signs are the same. So if I apply IH to both sides, because in real life, I don't know IH, I don't know U, I know IH of U, right? So I want to apply IH to both sides, super unrigorous, super heuristic here. And I want to take the inner product of IH of W. So I do some brute force energy estimate, and I get this. So I get a time derivative term, which I don't want. I get a term involving IH of AV, IH of W. IH of AV is totally fine because I know V, I can compute AV, IH is all good. And then IH of W, I can compute, we're all happy there. Minus mu IHW squared in L2 norm, that's great. This term, however, is a nightmare because I don't know if A and IH commute as operators, right? And then IH of BWV, well, that's a nonlinearity in U, which means I don't know if I can just put IH on each side, so this is just MS. So that feels kind of hopeless until we get some computations, but you can also think about this from a magnitude analysis. These are the terms I want to get rid of. Why can I do that? This first one will be argued computationally. The second one can be argued computationally and from a magnitude analysis. So we'll talk about it from a magnitude analysis first. Remember, W, think about it, we want W to be kind of small. So imagine nu2 is close to nu1. So W and L2 norm should be small, IHW and L2 norm should also be small because the H1 norm is small. So this is like order W and L2. This is order W, L2. The first and second terms are. The third term, so the first term on the right-hand side is order W squared, but it's weighted by a really large mu. So I'm going to consider him to be comparable to the order of the other two guys. But this last ugly term is order W squared in some sense. So maybe I can just drop that. Turns out, computationally, I can. So if I look at the mu IHW squared on the left here, this is with a bunch of different viscosities near 10 to the minus 3. So let's just track this red line here. So what's amazing about this theorem is not only does it say we're going to get a convergence, but we're going to flatten out at that error bar once we're more or less converged. So regardless of what's happening all over the whole thing, we still converge up to some error and it flattens out. So we can basically say, okay, time derivative 0, get rid of it. Now, what's important here is this mu IHW squared term, and then our ugly nonlinear term. Let's trace the last line, the bottom line here, with the red X or the blue circle. And we can see here that this goes around 10 to the minus 10, and this one's 10 to the below 10 to the minus 12, like 10 to the minus 13 or something. So in a magnitude analysis, this big nonlinear term doesn't matter. So we can completely ignore both of those terms and just equate the terms that we can handle, which is very nice. So once we do that, and I'm sorry because you guys can't see that, so there, okay, quiet enough so that you can actually see the formula. We can just equate these terms, and now it's just an algebraic solve for new one. So when we do that, we get this very simple algorithm. Nu 1 is approximately nu 2 minus mu times this quotient. Now, turns out that this is a simple algorithm. I can just implement it computationally. So I'm going to pick an incorrect viscosity. I'm going to set my initial condition to be 0 because I can. We're going to compute the data assimilation solution with the incorrect viscosity. So we're going to compute it until we converge, right? So converge up to that error, right? So the error bottoms out in some sense. Then I'm going to go in and I'm going to change the viscosity immediately. Just using the update algorithm to get a new nu2. And then so on and so forth until I converge fully. Turns out, following the blue line here, ignore the orange line for now. There's a time integral version that you can derive as well. But the blue line is what we're focusing on here. So we're going to have convergence, and then we're going to, error is going to flatten out, then we're going to change the viscosity, run the simulation again, so we'll have the exponential convergence, and then it'll flatten out, change the viscosity, exponential convergence, so on and so forth, all the way down to machine precision. So the dark blue line here is the one that is showing you the error of IHW2. And similarly, the dashed line, the dark dashed line is the error, but the dark blue line is the error of the U minus V. Yes. So not only is the error of IHW going to 0, the error of U minus V is going to 0 as well. So that's very cool. So this was finally published in 2020. And then of course, like, that's great, computationally ideal. How do we prove this? Turned out to be a pain in the butt until last year. And so it's been quite a while. So I tried looking at it for a while, and I got something for the Stokes equations, right, where I can ignore the nonlinearity. I can assume stuff moves everywhere. I assume IH is some sort of truncation into finite Fourier modes. You can just solve for everything explicitly and get the convergence. Turns out you need some sort of algebraic thing. And that actually was crucial to linchpinning this argument back in Lorenz land. So I had all but given up hope on energy estimates, because energy estimates with the time derivative and everything I wasn't sure how to deal with when I was a younger graduate student. Now it turns out to be that's the critical piece. So we're going to look at the Lorenz equations.
What did you say was the critical piece?
The critical piece is going to be energy estimates on the time derivative. So we need some extra regularity, which for Navier-Stokes we have. We'll mention that. But first, Lorenz equations. So Lorenz equations, we're going to look at this in the context. We also want to look at systems like Boussinesq, where we want to recover not only the viscosity for the velocity field, but also the kinematic, the thermal diffusivity term, kappa. So this gives us an intuition, maybe how to prove it theoretically, as well as what about multi-parameter recovery. So here I'm in ODE, right? So IH is supposed to be in space, so there's no IH here. There's no interpolation. We're just looking at, if I'm observing constantly in time, I'm just going to drive, if I have an incorrect parameter, I'm going to drive x tilde towards x. So original Lorenz equations would be without the mu1, mu2, mu3 terms. So from here, we can derive a recovery algorithm for each parameter in exactly the same way, sigma, rho, and beta. So just to clarify, let's do it again for Lorenz. So instead of taking the inner products with everything, you just multiply, right? You multiply out. So if I multiply, I'll take the difference of x tilde with x, look at the respective systems, and I'm going to multiply by u. So then I will take it here, multiply by u all the way throughout, do the same magnitude analysis. So I have the time derivative piece. I want to ignore for the same reasons, because I'm going to assume that the error is going to bottom out. And then this v minus u times u guy I don't particularly like. He's a error squared. These are just error and then error squared times mu. So I just want to end up equating. So these terms on the left-hand side in the bottom equation are going to be negligible. The ones on the right are going to be the ones we care about. So that to leading order, we can just do some basic algebra to recover our true sigma. So this is kind of a nasty little thing here, but we have to make an assumption that we're not dividing by 0, right? So this is basically an inverse problem in some sense. Don't know much about inverse problems. We kind of stumbled in on inverse problems when we're doing parameter recovery, which is kind of cool. So we have to make the assumption this is non-zero. We can do that. It's fine. Computationally, we can assume that. I believe that the set which that is zero is measure 0, but we didn't get to prove that. And it's probably out there somewhere. But the idea is that if I take mu large enough, then I can get algebraic convergence of the parameters to the true parameter. So the idea here is that I'm going to look at the system. I'm going to get energy estimates on I'm going to use energy estimates. I'm going to get estimates on K of T, where K of T is 1/2 U squared plus V squared plus W squared, right? So I can do that using our standard approach, and we can get it in terms of an exponential decay plus, of course, as expected, our delta sigma term. If for example, this is specifically for delta rho, delta beta 0. That's a simple case. So that's basically what we had from the Navier-Stokes problem, right? We had the exponential decay up to an error involving viscosity squared, particularly. Notice that the delta sigma squared shows up here. So the problem is now we also need estimates on the time derivative here. So we have L of t is less than or equal to the same exponential decay, and then our delta sigma squared. That's absolutely crucial. Uses bounds on the attractor for X, Y, and Z, all sorts of stuff. It's mostly just a lot of computations, it's not too different. But the reason we need these time derivative estimates is because we need to control, if we rearrange the top equation, right, that's how we derived the parameter recovery algorithm, is we looked at the U equation. So we need to look at the terms that we ignored, and we need to stop ignoring them. So the term that we have to estimate is going to be U dot. So we're going to do this in like an inductive, using an inductive argument. So if I have sigma n in the parameter recovery algorithm, I want to look at sigma n plus 1 minus the true sig, right? I want to look at the error between the true sig and not necessarily sigma n plus 1 minus sigma n. So I can write that down all day. So when I do that and substitute sigma n into our parameter recovery algorithm, I get the sigma n plus 1 minus sigma, and then I'll get this expression here. So I need to control this guy in particular. And when I do that, I can assume lower bound of y tilde minus x tilde plus our energy bounds. Basically what ends up happening is we get sigma n plus 1 minus sigma, so that's equal to some epsilon prime times sigma n minus sigma, where the size of this epsilon prime is controlled by the choice of mu. It turns out mu needs to be quite large for us to do that. So by induction, go all the way down to the 0 case. So think of epsilon prime is like 1/2 or something. You can get it to be just about anything depending on the future control mu. So thus we have algebraic and monotonic convergence of the parameters, which confirms the observations actually we saw in the blue graph and the blue graph. So that is really interesting. This argument holds identically if you put all the parameters together and you want to recover every single parameter. So for example, delta rho is non-zero, delta beta is non-zero. What's going to change in these bounds is now you're going to get plus some constant over mu2 times delta rho squared plus some constant times mu3 over mu3 plus delta, I think, times delta beta squared. And then you can do the same game there. It's not important. It's kind of ridiculous if you want to recover all 3 parameters, because that means you have to have let's see. Let me go back here. That means I'd have to have all the data, so then I could just solve directly for rho, sigma, and beta if I had all the data. But if I only have x and y, I can recover sigma and rho. If I only have y and z, I can recover rho and beta. If I have x and z, I can recover sigma and beta, so on and so forth. So I can have this kind of matching game. So I can recover all of those parameters. So now I'll go forward again. Back here. Okay, so yes. So this approach finally inspired the proof, one of the proofs, I guess I should say, of the 2D Navier-Stokes parameter recovery algorithm, assuming IH's projection onto low modes. It's recently accepted to nonlinearity by our co-author on this paper. There was a bunch of us that came together and had all these ideas, and they all coalesced, and we finally got the proof. And that finally led us into getting the proof for the Navier-Stokes algorithm as well. Also assuming that the denominator is non-zero. And we do need to have an argument explaining why that's the case, although I think that it's definitely true. We have intuition thereof, but we haven't actually proven it. I don't think it's proven it. So for this graph, what's nice about this is that now another problem that we have with this in real life. So I took a lot of the analytical stuff that I did, and I wanted to implement it in a real world simulation. Right, one that's been like atmosphere or ocean So I went to Los Alamos and I wanted to do that in their MPAS code. So I'll talk about that in a minute. But I noticed that it's quite difficult because their codes are very large scale. They have coarse grids because, you know, they're expensive computations. So what are the practical problems? And one of the practical problems I noticed is that we've been investigating theoretically where each of the, how robust the CDA algorithm is to each of these tweaks. Say we have an incorrect model, or we're only observing data on a subdomain, or we're just, we just have noisy data, or we just have discrete time. How do these things come when we pair everything up? That's really important. So how does that, how far can we push the algorithm to break it? So that's kind of our next step. This is a place in which to start with that. So this graph here is for Lorenz. We did parameter recovery, but now with observations every 500 time steps. So instead of doing the continuous observations like we assumed in the theory, now let's say we're not observing data at every time step. That's a lot. So turns out we can still get all the convergence even with discrete time, which is very encouraging. But when we implemented that mu, so let me go back to the parameter recovery algorithm. So this bottom one here, for example, this mu right here is mu1 in the parameter recovery algorithm. When we have discrete time, it cannot be the same as the mu that's driving the system. We're not entirely sure why yet. We have arguments just for the discrete group from a discrete perspective, but analytically, I'm not entirely sure how to fix that yet. But I've got 1400 days going on. I want to do that at some point, but we've got a lot to investigate here. There's so much to look into. So we can, if we make that smaller in the computations, we still get the convergence. Which is fabulous. If we have only observations, we get the multi-parameter recovery. If we have observations in X and Z, X and Y, Y and Z, so on and so forth. Another thing, we wanted to look at parameter recovery with observations and noise. How does it work? Turns out we still get the recovery up to an error determined by, so this is no error, so we see the 10 to the minus 15, 10 to the minus 14, close enough to 10 to the minus 16 for our taste. And if we introduce some sort of error, then we get convergence up to something determined by that error. So 10 to the minus 5, 10 to the minus 5 here. So with that, I think we have a bit of time to move forward here. Yes, so with that, that's kind of the direction we need to go next as a community is, okay, we've got all these ideas and how the algorithm itself is robust to all these changes. How far can we push and combine all those changes? That's at least one direction we definitely need to go. So one of the applications that I worked on in the last couple of years, and I'm still working on because, you know, simulations, global ocean simulations cannot resolve all physical processes due to computational expense. And these largest eddies have a length scale directly proportional to the Rothby radius of deformation. We have eddies spin off of larger eddies, leading to eddies at a smaller length scale, and then you have this, that leads to this classification of different model resolutions. And it's extremely vague, and it's not rigorous at all, but it's eddy permitting versus eddy resolving. So if you basically, you're just going to see one type of eddy in the eddy permitting, and in the eddy resolving, you should see eddies spinning off of the larger eddies, and we hope that most of the time they can kind of figure out if they adjust a little bit deeper down if we're going to get any more eddies. And that's what they call eddy resolving, but that's difficult to quantify because, you know, for these big ocean simulations, how are we going to go make our resolution go all the way down? We can do this in some subcases. Current fixes on this problem are parameterizations, so they can basically work on the subgrid scale effects of the problem, and they can incorporate some of the subgrid scale effects into the problem on the large scales. So if you were at Baylor Fox-Kemper's talk last week, he described a lot of the parameterizations. He did a fabulous job in that talk. I actually want to go back and watch it a couple more times because it was really great. He had a list at the end of all the different parameterizations that are implemented in global ocean models. Another approach is to use variable resolution models. So in some places in the ocean, you might not, the subgrid scale dynamics might not be as important. Maybe you don't have, you're not against the coastline, so you're not getting all these boundary effects, all this sort of thing. So you might need more resolution. You need more resolution along the coastline, but maybe not smack down in the middle of the Atlantic, for example. So our goal was to assimilate horizontal velocities, temperature, and salinity from a high resolution eddy resolving simulation into a low resolution eddy permitting simulation to incorporate the effects of eddy transport. Think about it like this. We were thinking of Reynolds number could be a proxy for using numerical diffusion. We showed with the parameter recovery that we can get convergence of the data simulation algorithm up to an error involving the errors in the viscosities, right? Which is analogous to the Reynolds number. So maybe there's something that could be happening here. Can data simulation help us recover some fine scale features? And, or at least the effects of fine scale features. And so our metrics were eddy kinetic energy, mass transport, isotopic effectivity, and root mean square error. And this was our test case. I don't want to focus on it too much because this is a math seminar. And basically the idea is I want to say that we needed a test case that gave us these eddies, right? So what happens here is you look at these things called gyres. You put these two gyres together, and what happens is they interact to create a baroclinic jet. They make these big eddies, and off the big eddies spin the smaller eddies. This is what's called a simulating ocean mesh scale activity test case. So what I really wanted to focus on though is I was wanting to understand, okay, in real life, data simulation is a big part of these applications. So when you want to model the real world, how do we do this? How do we use the observations? Turns out there's this concept called reanalysis data, which is as close to a nice grid like this as possible, where we're taking the observations and we're kind of filling in the holes. So this is a whole suite of data called reanalysis data. For our purposes, we want to do this in a quasi-idealized setting. So we ran an 8-kilometer resolution simulation and took observations on a rectangular grid, because that's how we see reanalysis data. And we wanted to use that data and assimilate it into a low resolution, ours with 32 kilometer resolution simulation. Now, the problem with this is that people have gotten really clever and used very clever discretizations and very clever grids. This one uses Verona tessellation. It's the hexagonal type grid. It's got this dual structure. And I don't know much about it because I didn't too, but what I did notice that's really important is that one, if you're taking these observations and they're rectangular here on this rectangular grid, it's not nested inside of this hexagonal grid. That's problematic. If I want to look at IH of V minus IH of U, I need to be looking at V on the observational grid, right? So that means I need to know V everywhere in space. Theoretically, I know V everywhere in space. And in computationally ideal scenarios, I'm going to take my discrete grid and I'm going to take the observation as a subset of that, because why wouldn't you? So, but in real life, in these applications, in order for other things to work, that's not the case. So observations, we want to take IH, we want to take U observed on here, and interpolate it to the grid, right? So that's what we want to do. But if we just leave this, the V solution here, then we're looking at, if we go back to the system, so let me draw this, write this on the board here. I have dV, dt, for example. Instead of IH of V minus IH of U, I am now just considering V minus IH of U. So then when V and U are getting close, even if they match up exactly, the physics isn't going to be the same. In fact, this has become a term that no longer helps you but hurts you. It's introducing new error, specifically V minus IH of U, and it's being magnified by mu. So that's problematic. Turns out that, so this method is very similar to something called nudging, our original data simulation algorithm. Very similar to something called nudging. So instead of looking at IH of U minus IH of V, the original version just compared the points at the discrete grid points. So if I was looking at U on this right-hand grid and V on this right-hand grid, I would just subtract them at the particular points now and just use them on this grid. And I only look at the points. I wouldn't actually interpolate it out everywhere. So I'm basically not spreading the information to the whole grid. Another version is, in practice, of course, that's annoying if I'm just wanting to look at V minus U on this grid and assimilate it here with no interpolation. So I need to say, okay, I'm going to take IH of U and interpolate it here, but this V I don't want to mess with because that's a lot of computational work. So I'm just going to leave it, which puts you back in the case of V minus IH of U. This is a very common method of nudging, totally fine, computationally efficient, etc. But mathematically, it's not accurate. So what we need to do is we need to take V. We're assuming that our observation grid is coarse with respect to our model grid, right? So if I approximate V on the observation grid, basically do an IH out and an IH back in, then I have IH of V, but it'll be closer to IH of V than just V itself. That's the idea. So we wanted to verify that that was the case, obviously, right? So I don't want to go over too much. So we've got time, okay. So if we look at this graphic here, we worked on isopycnal vertical layers. That's basically surfaces of constant density. So this up here is our 8 kilometer reference. So this is our high res simulation. So this is the data we're assimilating into the data assimilation runs at low resolution. Notice using the eyeball norm, these look all the same and they look very different from the 32 kilometer control system with no data assimilation. So if I'm quiet, hopefully the thing will go away and you'll be able to see it a little better.
Which one is the 32 kilometer resolution? Is there a picture here?
This
The
one.
bottom one. All right.
Yeah, that's fine. So you can actually see it.
Oh, okay. Only the top row is 8 kilometers.
Mhm.
The rest are.
So I don't know if you can see here. Maybe if I can exit out so you can see it a little bit better. Here we go. Okay, so you see one big eddy here, right? One massive eddy. There's no spin-off really. There's some sort of behavior going on here, but basically all this energy is being concentrated in this one big eddy.
The plots are of vortex speed.
This is the. Do you remember? I'm pretty sure this is just the kinetic energy.
Okay.
Is there a physical reason for an
Lost
eddy to
energy.
concentrate?
Yes, speed contours. Sorry, speed contours.
Is there a physical what is the reason behind that eddy to be concentrated in that region?
Oh, it's because the resolution of the model is too coarse.
Okay.
So basically the other eddies can't spin off of it. So you see here with 32 kilometer, these are interpolated to a coarser grid, but at least we're seeing the effects of the 8 kilometer reference, and we're seeing it spreading across even in the large scale, the effects to the rest of 32 kilometer just via data simulation. So that was cool. That's encouraging. We're doing another test right now where we're taking this data and we're not going to interpolate it linearly. We're going to interpolate it constant piecewise, and we're going to see if that changes anything. Because we might be bleeding some effects of the 8 kilometer into the 32 kilometer that we shouldn't yet, just based on observation. That's an argument I've been given. I'm not sure if I 100% believe it, but something we're continuing to fix.
Meaning that the interpolation can be too accurate.
Not too accurate, but it could be taking the effects that we're quote missing and feeding them into the actual points themselves. I'm gonna renege this up on that and I'll argue it a little bit more later because it's a little bit complicated. We had to talk it back and forth. But but this is the critical point. So this V minus IH of U term that occurs in the original, in the standard grid nudging, because I don't want to do the back and forth interpolation because it's expensive, understandable, you have to pick your battles. How much of a difference does it make? And it turns out that if I'm observing data on a finer grid, it makes a little bit of a difference. I think it's like 10 to 20% improvement in the root mean square error. But if I observe on a coarser grid, it's up to 30% change in root mean square error. So it actually makes a relatively significant difference. I'd have to test in other suites as well, but it does indicate that doing that back and forth interpolation actually reduces your error rather than just considering V and not messing with extra computation. So from here, future current work is, of course, can we somehow recover the forcing function F? Our research group is working on that right now. Been trying to work on that for on and off for a long time. The group has, so that's still in the works. It's quite difficult. We also want to look at applications to multi-physics equations. There's an S. This is something that's been on my plate, on my mind for a while. I've derived multi-parameter recovery algorithm for the business system. In the dimensional case, I want to figure out how to do it in the non-dimensional case, because everything, as you noticed before, is linear in the parameters, not non-linear. When you non-dimensionalize business, you get a really transparental and their product, and so you have to, when you're trying to do magnitude analysis, you're like, wait, what's so there's more work to do there. We want to look at a model bias study for global ocean, and I want to compare it to other statistical data assimilation methods, because those are important to be used in, those are used everywhere in real data assimilation settings. So Mike Cullen, I don't know if you guys were in the Turbulence seminar, he was here last week. He's been doing 40 bar at the RidgeNet for a while. We had a nice discussion on what is the difference between deterministic models and how that relates to data assimilation, how accurate we eventually get with our data assimilation. But I think it's, to leave it off on a note, the statistical data assimilation is a lot longer to percolate because it's dealing with the noise directly. That's going to come from the measurements, which is very important. And so it's going to make it as accurate as possible for linear models. But it's very hard to prove things there. There's only a handful of papers that actually show some sort of convergence. And the one that finally showed it for a version of common filter was in 2016 by Maida and Kelly. And before that, I think the closest thing they got to was in 2013 by Cody Law and Company. So we're having them in a scientific conference later this week. So we're looking forward to our discussions on that to see what these comparisons are. But the nice thing coming at it from the simpler perspective is it might give us some insights also into the more complicated statistical data assimilation methods. So we've got a lot of discussion between the communities to go, and a lot of progress in both directions. So thank you all for coming today.
Just the last thing you mentioned about the proofs of the common filter case. What was this for Navier-Stokes?
So I'm still wondering about that, because I think yes, they're for Navier-Stokes type, but I think they make an assumption as well that I have to verify. And I think they might be linearizing something, which might make it still not quite the same amount of convergence. It's very difficult to parse because it's extremely complicated, which is why nobody's been doing it, or they've been doing easier, they've been looking at other types of convergence that we need to consider for these methods as well.
And you said this talks on this later this week.
Yes, at the Scientific conference, I'm organizing it with Joshua Hudson, my collaborator. So thank you to all my collaborators. They are awesome and wonderful, wonderful people. If you ever get a chance to work with them, they're fabulous. And so that's tomorrow. I believe the session is called Theory and Applications in Data Assimilation. I can look it up for you if you would like to attend. This week is tomorrow and Friday.
Can I ask a couple questions?
Yeah, absolutely.
So I think I understand now this. I was a little confused about the domain and the range of this operator IH.
Oh, yes.
But so is it correct that it encapsulates both the measurement and the interpolation? Like the measurement on the coarse grid and then the interpolation back out to the full domain?
Oh, I see what you're saying. So
because you have it appearing like being added and subtracted with the unknown variables being u.
yes. So IH is a linear operator that maps. So theoretically, we're thinking about it like IH.
Can you use a different color?
Good point. What am
Yes.
I? Purple is not a good idea. White. Okay. So IH maps H1 to L2. So we're kind of thinking about it in this abstract sense. It's taking U
Yeah.
and it's interpolating it on this space. If you want to read more about the interpolant stuff, I know what I need to know to make the analysis run. So if you want to know more about it, though, you can read about it in final textbooks. I can give you a reference that will give you more details here, because it can also take spaces from H2 to L2.
Okay.
So this also all works so then with finite element type interpolations.
And like the domains of those function spaces are the same.
Yes. Oh, yes. Yes.
Cool. And
So
then,
this should be of omega.
Yeah.
I'm working in periodic Dirichlet
You saw the
Usually
equation
periodic.
on Omega.
Omega's a Taurus.
Let's see. So then in the thing where you were doing estimating the viscosity or the parameters for the Lorenz system, can those parameters be like spatially varying? Possibly.
I don't
Or
see
is
why
there-
not.
Does this analysis not consider it?
I don't see why not. You'd have to give me a model and I'd have to look at it and see if it would, I'd have
Yeah.
to see if, drive the heuristic, see if it would work. Again, the linearity in the parameter itself would be kind of important. So I'd have to, So, like,
Oh,
so I was saying with Boudinesque, if I want to non-dimensionalize it, I find it a bit trickier to derive a parameter recovery algorithm because its Prandtl time really appears in the velocity equation. Whereas if I'm just wanting to recover the dimensionalized version, nu and kappa, that's fine because velocity equation is linear in nu and the thermal equation is linear in kappa.
okay, so you can only.
As
You can
far
only
as I know,
recover
I could
parameters
be-
where the
I could-
governing dynamics that are linear in those parameters.
As far as I can write down right now, that's new work, not yet explored. New directions, but if you want to talk about them more, we can. If you give me a specific equation, I might be able to write something down.
Don't put me on the spot.
Any other questions from the audience or?
I have one more, but if someone has a question.
I was gonna say, can transcribe the video so Zoom can hear me. For the Zoom participants, if you unmute yourselves and have a question that you want to ask, I believe we should be able to hear you through the speakers. You want me to do that if you like. Yeah.
Yeah, so back to I think it was the Reynolds number recovery, I think. You were doing some dominant knowledge analysis,
Yes,
right? To say, okay, we've already converged far enough that this time derivative is vanishing and this other one is second order error.
Mhm.
Is it possible, do you think, to do a higher order expansion in like introduce an explicit small parameter and go to first order or second order in that, and maybe get a slightly more accurate
maybe.
formula?
I mean, I haven't really thought about that. Maybe you could do that. That would be really interesting. I mean, if it works at this order, that might not be necessary, but it might be necessary down the road when we're looking at introducing all these robustness checks, right? So discrete time, noisy data, et cetera, So that might be useful down the road.
Yeah,
I'm not sure yet here, but
the results even at this rough argument were very impressive. We were able to convert so fast.
it was
Like that's stereotyping.
really surprising, very, very cool. We were very excited when we saw it. It took a cool paper into a, wow, that's interesting paper. So this is just some of the work I've been doing. I also have 2 other papers on a variation, nonlinear variation of this analytically and on sensitivity analysis as well. So if you're interested in those robustness considerations, you can also.
How does the recovery of Reynolds difference work? Reynolds is large or something. What if one of my wrong guesses is that it's actually C?
Well, that is a little annoying in terms of computations because Euler versus Navier-Stokes. but-
Is there like somewhere like all this you have to say that
So I don't think so, because this actually relates to the sensitivity paper. So I don't know how it works with the parameter recovery algorithms. We haven't derived that yet, but if we're looking at the sensitivity with respect to viscosity, specifically, we can show that the sensitivity equations of so if we take Navier-Stokes, take the derivative with respect to viscosity, and the viscosity is set to be 0, we can show that you can basically rigorously derive. Basically, you take the derivative of Euler with respect to a non-existing viscosity. And then you can show that difference quotient in Navier-Stokes using Massimootti's work with sufficient irregular initial data will converge to the sensitivity equations for Euler with respect to viscosity. But I don't know exactly how that works with respect to the parameter recovery algorithm. That's not something we've looked into yet. I mean, I'm also not sure, do you have any idea in terms of application where that might be useful?
No, not specifically, but with, so this is with periodic boundary condition. So it's maybe if you have the certain stuff like you're not bounded below by
Which is why Massimootti's work is okay for sensitivity analysis.
I had a completely different question to the Lorenz.
Sure.
So it's finite dimensional. So you just so then I'm trying to if you understood what you're saying very correctly. So now I don't have an I8 because it's already finite dimensional. But the attractor is lower than right. It's not full. From the figure that's but the point is, can you get away with if you had some 2D coordinates on this or at least locally or something, you'd be able to only have mu act on to the or whatever the dimension of the attractor is, and not the full nudge less by just nudging.
Oh, so these are all tunable. So I can shut off mu I at any point that I like. The problem is because if I do mu on every variable, there's literally no point. I already have all the data, right? Because x and y and z are the whole thing, right? So if pretend mu2 is 0, mu3 is 0,
yeah,
then x is everything. So I'm fine. I can just, if I have x, y, and z, I can just plug and chug and get the parameters directly. I know what they are. So assimilating all three is trivial, and we don't need to use this algorithm. It's over.
But you can switch one of them at a time?
You can switch off and on as many of them. It's just leave a light switch panel. It's fine.
Okay, so if you only have one of them on, that will only do that.
Yeah, if you have one of them on, well, careful. If you only have one of them on, you can recover the solution
Right,
to
so
that
yes,
equation.
I was thinking about the solution, but for parameters.
Same with parameters. So parameter, notice the recovery algorithm, the way I derived it for sigma, for example, came explicitly from the first equation. Rho came explicitly from the second equation. Beta came explicitly from the third equation. So I need, if I want to recover beta, I need to be observing z data. If I want to recover rho, I need to be observing y data. If I want to recover sigma, I need to be observing x data. So if I know the correct parameters, sigma and beta, then I can just turn on mu2 and I don't need x and z. So I basically it's telling me that if I want to recover, if I only have a guess at rho, I need to be observing y. If I want to recover sigma, I need to be observing x. If I want to recover beta, I need to be observing y. In this particular setting, there might be something else you can do. I'm not sure yet.
And to recover the solution, but I guess the earlier stuff, so the easier version, I guess. You only need one of them to be turned on. One of them used to be on.
Yeah, you only need one of them used to be on for Lorenz. Yeah, for Navier-Stokes, there's only one, right?
Yeah. But there's H, which is however many. Right, like
so
here, if I only have, I guess this is the parallel I was trying to draw. It's just that here you're only if only one of the new I is on, then I'm only getting one scalar at a step, and in Navier-Stokes I'm feeling like 1 over H something scalar. It's taking smaller.
yes. So you can kind of think of it. So here, obviously, you only have like one data point, right? So in Navier-Stokes, you have more than one data point. So, but you'd be assimilating some interpolation of that continuously in space. You're really in Banach space. Right here, you're just a point. There, it's like a whole spatial object. Yeah, this is kind of just one scale, right? So I mean, we were having struggle with proving it in first, so you had to go somewhere. So that was here. Yeah.
No, I think it's needed. Show this.
Yeah. So what was I going to say about that? So, oh yes, H and mu are intertwined, so you can't just tune H without tuning mu and vice versa. Because basically what happens in the energy estimates is you get a mu times H out because the bound you have on the turbulent operator that's acting in this space. is dependent upon basically the resolution. So mu times h has to be 1. So has to go so on.
Any other questions in the room or on Zoom? I'm not seeing anything, so I guess let's thank Elizabeth again.
Thank you for having me.
And our next J seminar is in about a month on April 13th.